You think you know what matter is made of. Particles, little balls, tiny spheres bouncing around, atoms made of smaller particles, protons, neutrons, electrons, those made of even smaller particles, quarks. It's particles all the way down, right? Wrong. Completely, catastrophically, fundamentally wrong. And what I'm about to tell you is going to destroy everything you think you know about reality. Particles don't exist, not the way you imagine them, not little balls, not tiny spheres, not objects at all. What you call a particle is something so strange, so alien to everyday experience that physicists spent decades arguing about what it even means. And most of them still can't explain it properly. Let me show you what's really going on. Pick up any object, a pen, a rock, your phone. You think it's made of stuff, material, substance. You think if you zoom in far enough, you'll find the building blocks, the tiny Lego pieces that make up everything. First you see molecules. Zoom in more, atoms. Zoom in more, a nucleus with electrons around it. Zoom in more, protons and neutrons. Zoom in more, quarks, and you think at some point you'll hit bottom. You'll find the actual stuff, the real material, the thing that everything else is made of. You won't, because there is no stuff. There is no bottom. What you find when you zoom in far enough is not particles. It's fields. And fields are not things. Fields are something else entirely. Let me explain what I mean. You've heard of magnetic fields. You've seen iron filings arrange themselves around a magnet. You've felt two magnets push against each other through empty space. That's a field. It's not a thing. It's not made of particles. It's a condition of space itself. Every point in space has a value, a direction, a strength. The field tells you what would happen to a magnetic object if you put one there. But the field itself is not an object. It's more like a property of space, a way that space is configured. Now here's the thing that's going to break your brain. Everything is fields, not just magnetism. Everything. There's an electron field that fills all of space. There's a quark field, a gluon field, a photon field, a Higgs field. These fields are everywhere, always. They permeate every point in the universe. And what you call particles are not things floating in these fields. The particles are the fields. They're ripples, excitations, disturbances in the fields. Think of the ocean. The ocean is water, everywhere, continuous water. Now imagine a wave. The wave is not a thing separate from the ocean. The wave is what the ocean is doing. It's a pattern of motion, a disturbance that travels through the water. You can point at a wave. You can measure its height. You can watch it move, but you can't pick up a wave. You can't separate it from the ocean. The wave is the ocean, doing a particular thing in a particular place. That's what an electron is. The electron field fills all of space. It's everywhere, always. And an electron is a ripple in that field, a localized disturbance, a wave packet. You can point at it, you can measure its properties, you can watch it move, but you can't pick up an electron like a tiny ball, because it's not a ball. It's a pattern in a field. The electron is the electron field, doing a particular thing in a particular place. This is not a metaphor. This is not an analogy. This is what quantum field theory actually says. And quantum field theory is the most precisely tested theory in all of science. We've confirmed its predictions to 11 decimal places. 11. That's like measuring the distance from New York to Los Angeles and being accurate to within the width of a human hair. The theory works. And the theory says particles are field excitations, not things, patterns. Now you're thinking, okay, fine. So particles are waves in fields. There's still something. They still exist. I can still point at an electron and say, there it is. Wrong. Again, because here's where quantum mechanics makes everything worse. You can't point at an electron and say, there it is, because the electron doesn't have a definite location until you measure it. Before measurement, the electron is not in one place. It's not in multiple places. It's not anywhere. The question, where is the electron, has no answer. Not because we don't know, because there is no answer. The electron doesn't have a position until the act of measurement creates one. This is not philosophy. This is not interpretation. This is what every single experiment tells us. We've tested this thousands of times. The electron is described by a wave function, a mathematical object that tells you the probability of finding the electron in various places if you look. But before you look, the electron is not hiding in one of those places. The wave function is the electron. That's all there is. Let me make this concrete. There's an experiment called the double slit experiment. Feynman called it the only mystery of quantum mechanics. Everything else, he said, is just variations on this theme. Here's how it works. You have a barrier with two narrow slits. You shoot electrons at it one at a time. Each electron goes through the barrier and hits a detector screen on the other side. Where does it land? You'd think, obviously, the electron goes through one slit or the other. It's a particle. It has to go through one of them. And it should land in one of two spots corresponding to the two slits, like throwing tiny balls at a wall with two holes. That's not what happens. When you run this experiment, shooting electrons one at a time, waiting between each one, you get an interference pattern, bands of light and dark. The pattern you'd expect if waves went through both slits simultaneously and interfered with each other. The pattern you get when ocean waves pass through two gaps and overlap on the other side. But wait, you sent single electrons, one at a time. How can one electron interfere with itself? How can it go through both slits? Here's the answer that will destroy your intuition. The electron doesn't go through one slit. It doesn't go through both slits. It doesn't go through the slits at all, not in the way you mean. The electron as a localized particle doesn't exist during the experiment. What exists is a wave function, a field excitation, and that wave function evolves according to the Schrödinger equation. It spreads out. It goes through both slits. It interferes with itself. And then, only when it hits the detector does it collapse into a definite position, a single dot on the screen. The electron wasn't a particle that traveled through space. It was a wave function that evolved, spread, and then collapsed. The particle only appeared at the moment of detection, the moment of measurement. But here's the truly disturbing part. What counts as a measurement? What causes the wave function to collapse? Nobody knows. This is called the measurement problem, and it's been haunting physics for 100 years. We don't know what triggers collapse. We don't know why observation matters. We just know that it does. Some physicists say consciousness collapses the wave function. That's probably wrong. Others say the wave function never collapses. It just branches into parallel universes. That's the many worlds interpretation. Others say there are hidden variables we haven't discovered. That's mostly been ruled out by experiments. Others say the wave function is just information, not reality. And others say we should shut up and calculate because the questions don't have answers. The point is this. What you call a particle is not a little ball that exists and moves through space. It's a mathematical object called a wave function that evolves according to equations and sometimes, under certain conditions we don't fully understand, manifests as a localized detection event. The particle is the detection, not the thing being detected. Now, let's make it even weirder. Let's talk about how particles are created and destroyed. If particles were little balls, they'd be permanent. You can't create or destroy a ball. You can break it into pieces, but the pieces still exist. The stuff is conserved. But particles aren't like that. Particles are created and destroyed constantly. An electron and a positron meet. They annihilate. Both particles disappear completely. In their place, two photons appear. Two new particles, created from nothing except energy. Where did the electron go? Nowhere. It stopped existing. Where did the photons come from? Nowhere. They started existing. This happens constantly. In particle accelerators, we smash protons together and create hundreds of new particles, particles that weren't there before. Particles with more total mass than the original protons. Where does the mass come from? From energy. E equals mc squared. The kinetic energy of the collision becomes the mass of new particles. This only makes sense if particles are field excitations. The electron field can be excited or not excited. When it's excited in a certain way, we call that an electron. When the excitation disappears, the electron disappears. When a new excitation appears, a new electron appears. The field is permanent. The particles are temporary patterns in the field. Think about sound waves. A sound wave is a pattern of compression in air. You can create a sound wave by clapping. You can destroy it by letting it dissipate. The air doesn't get created or destroyed, just the pattern. Same with particles. The fields are permanent, fundamental everywhere. The particles are temporary, derivative, local patterns. Here's where Feynman comes in. Feynman developed a way of calculating particle interactions called Feynman diagrams. These diagrams show particles as lines traveling through space and time. Electrons interact with photons. Quarks exchange gluons. It looks like a picture of particles bouncing around. But Feynman knew the diagrams weren't pictures of reality. They were calculation tools. Each diagram represents a mathematical term in an infinite series. To get the right answer, you have to add up all possible diagrams, all possible ways the interaction could happen. And I mean all, including diagrams where particles go backwards in time, including diagrams where particles pop in and out of existence, including diagrams that make no classical sense at all. Feynman understood that the diagrams didn't represent particles moving through space. They represented contributions to a probability amplitude. The real physics is in the fields and the mathematics. The particles are just a convenient way of talking about certain terms in the calculation. In his lectures, Feynman was very clear about this. He said, we don't know what an electron is, we know how it behaves. We know how to calculate what it will do. But we don't know what it is in any deeper sense. Is it a wave? Is it a particle? Is it something else entirely? The question might not have an answer. It might be like asking, what is the sound of one hand clapping? A question that seems meaningful but isn't. Now let's talk about something even stranger. The vacuum. You think empty space is empty. Nothing there. No particles, no fields, nothing. Wrong. Completely wrong. The vacuum is seething with activity. Here's why. The uncertainty principle says you can't know both the position and momentum of a particle exactly. But it also says you can't know both the energy and the time duration of a process exactly. If you look at a very short time interval, the energy becomes uncertain, very uncertain. And energy can become particles. E equals mc squared. So in very short time intervals, particles can pop into existence out of nothing. They have to pop back out quickly before the universe notices the energy violation. These are called virtual particles. Virtual particles are everywhere. The vacuum is constantly producing electron-positron pairs that exist for a tiny fraction of a second and then annihilate. Photons appear and disappear. Even gravitational fluctuations bubble up and vanish. The vacuum is not empty. It's a roiling sea of temporary particles, constantly appearing and disappearing. Can we detect these virtual particles? Yes. The Casimir effect put two metal plates very close together, closer than the wavelength of most virtual photons. The plates restrict which virtual photons can exist between them. Fewer virtual photons between the plates than outside, this creates a pressure difference. The plates get pushed together by nothing, by the difference in virtual particle density. We've measured this effect. It matches the predictions exactly. Virtual particles are real. The vacuum is not empty. And this only makes sense in the field picture. The vacuum is the ground state of the fields, the lowest energy configuration. But even the ground state has fluctuations, quantum jitters. The fields never sit perfectly still. Here's another thing that will bother you. Particles of the same type are identical, not similar, not very alike, absolutely, fundamentally, perfectly identical. Every electron in the universe is exactly the same as every other electron. Same mass, same charge, same spin, no variation, no individuality. You can't paint one red to tell it apart. You can't scratch a notch in it. Every electron is the same electron. Why? If electrons were little balls made in some particle factory, you'd expect slight variations. Manufacturing tolerances, wear and tear, no two would be exactly alike. But electrons aren't manufactured. They're excitations of a single field, the electron field. And the field only allows certain excitations, certain modes, like how a guitar string only vibrates at certain frequencies. The notes it can play are determined by the string's properties. Every note of the same pitch is identical because they're all the same mode of vibration. Electrons are identical because they're all the same mode of the electron field, not copies of each other, literally the same thing, the same pattern occurring in different places. This has profound implications. If you swap two electrons, nothing changes. Nothing detectable changes. Nothing changes, period. The universe is exactly the same because you haven't swapped two different things. You've just relabeled the same thing. This is why quantum statistics works. Bosons like to pile into the same state. Fermions refuse to share states. These behaviors emerge from the mathematics of identical particles, from the fact that swapping identical particles either changes nothing or flips the sign of the wave function. And those behaviors only make sense if particles are field excitations, if they're all instances of the same underlying field doing the same thing. Let me tell you something else that will disturb you. Particles don't have definite properties until you measure them. You think an electron has a position. Wrong. It has a wave function that encodes possible positions. You think an electron has a momentum. Wrong. It has a wave function that encodes possible momenta. You think an electron has a spin direction. Wrong. It has a superposition of spin states. Before measurement, the electron is not spinning up, it's not spinning down, it's not spinning up and down, it's not spinning at all. The concept of spin direction doesn't apply. The question, which way is it spinning, has no answer. This is hard to accept. Our intuitions evolved in a world of definite objects with definite properties. Rocks don't superpose. Chairs don't interfere with themselves. But that's because rocks and chairs are made of so many particles that quantum effects average out. The weirdness is still there. It's just hidden by statistics. But at the fundamental level, properties don't exist until measurement creates them. The electron doesn't have a position. The measurement creates a position. The electron doesn't have a momentum. The measurement creates a momentum. The particle is not revealed by measurement. The particle is created by measurement. What exists before measurement? The field, the wave function, the quantum state, mathematical objects that don't correspond to any classical picture. We can calculate with them. We can make predictions, but we can't visualize them. We can't say what they are in everyday terms, because everyday terms don't apply. Now let me tell you about something that really bothered Einstein. Entanglement. You can create two particles that are entangled, correlated in a quantum way. Let's say two electrons with opposite spins. You don't know which is up and which is down, but you know they're opposite. Now separate them. Send one to New York. Send one to Tokyo. They're still entangled. Measure the spin of the New York electron. Let's say it's up. Instantly, the Tokyo electron becomes down. Not was always down and you just discovered it. Becomes down. At the moment of measurement in New York, the quantum state in Tokyo collapses. Einstein called this spooky action at a distance. He thought it proved quantum mechanics was incomplete. There must be hidden variables that determine the outcomes in advance. The electrons must decide their spins when they separate, not when they're measured. He was wrong. We've done experiments. Bell's inequality. If there were hidden variables, the statistics of measurements would have to follow certain rules. Quantum mechanics predicts different statistics. We've tested this. Quantum mechanics wins. There are no hidden variables. The spin really is undetermined until measurement. But here's the thing. This doesn't violate relativity. No information travels faster than light. You can't use entanglement to send a message because the result of your measurement looks random to you. You don't know if the other particle was measured first. You can't control what results you get. The correlation only appears when you compare results, when you bring the measurements together, and that comparison can only happen at the speed of light or slower. So causality is preserved, but locality is not. What happens here instantly affects what's possible there. Not through any physical signal, through the collapse of a shared wave function. This only makes sense if particles are field excitations. If the two electrons are really two aspects of a single quantum state, a single wave function describing both. When you measure one, you measure part of the whole, and that changes what's possible for the other part, not through any signal, through the mathematics of quantum states. Let me bring this back to what you're made of. You think you're made of particles, atoms, molecules, cells. Wrong. You're made of field excitations. You're a pattern in the quantum fields. An incredibly complex, dynamic, self-sustaining pattern, but a pattern nonetheless. The atoms in your body are mostly empty space. The electrons are smeared wave functions. The quarks are confined field excitations. The gluons are popping in and out of existence constantly. The Higgs field is giving mass to everything. The electromagnetic field is carrying forces. The gravitational field is curving space-time. You're not stuff. You're a symphony of fields, a jazz improvisation in quantum field theory, a temporary arrangement of excitations in the fundamental fields that will eventually dissipate when you die. But here's what's amazing. That pattern thinks, it feels, it asks questions about its own nature. You are the universe understanding itself. Field excitations that got so complex they became conscious. And now those excitations are contemplating the fields they're made of. That's not depressing. That's miraculous. Not in spite of being field excitations, because you're field excitations. Because the deepest level of reality is not dead matter. It's living mathematics, dynamic patterns, constant creation and destruction. The universe is not a collection of things. It's a process, an activity, a becoming. Let me tell you what Feynman said about this. He said the beauty of the world is that it can be understood, that there are patterns, that there are laws, that the same equations describe electricity and magnetism and light, that the same quantum field theory describes electrons and quarks and photons. The universe isn't arbitrary. It's structured. It has rules. And those rules are beautiful. Simple at the deepest level, elegant, unified. We don't know why the rules are what they are. We don't know why there are rules at all, but we know there are rules, and we can discover them. And every time we discover a deeper rule, we find more beauty, more elegance, more unity. Particles don't exist, not as little balls, not as things. They're excitations, patterns, mathematics made manifest. And that's not a disappointment. That's the deepest insight physics has ever achieved. The universe is not made of stuff. It's made of stories, mathematical stories. Quantum field theory is the language those stories are written in, and particles are characters in those stories. Not fundamental, not permanent, but meaningful, dynamic, alive. Here's what I want you to take away from this. The next time you look at your hand, don't think atoms. Think fields. Think of electron fields and quark fields and gluon fields, all vibrating, all fluctuating, all interacting. Think of virtual particles popping in and out of existence. Think of wave functions collapsing every time you observe something. Think of entanglement connecting separated particles. Think of the vacuum seething with energy. Your hand is not solid. It's not made of stuff. It's an incredibly stable pattern in quantum fields, a pattern that's maintained itself for years, a pattern that eats and breathes and moves to maintain its structure, a pattern that thinks and feels and wonders about itself. You are not a thing. You're a process, not a noun, a verb. The universe is not a collection of objects. It's a happening, and you're part of that happening, the part that knows it's happening. Particles don't exist, not the way you thought. But what does exist is far more interesting. Fields that fill all of space, excitations that live and die in those fields, patterns that maintain themselves against entropy, complexity that emerges from simplicity, consciousness that emerges from complexity. That's the universe. That's you. That's everything. not stuff, process, not things, happenings, not particles, fields. And the fact that we can understand this, the fact that human beings, ourselves made of field excitations, can discover the mathematics of fields, can peer into the quantum realm and see what's really there, can test our theories to 11 decimal places and find they work. That's the real miracle. Not that particles exist, they don't. The miracle is that the universe has structure at all, that the structure is knowable, that we can know it. Feynman spent his life exploring that structure. He invented new mathematics to describe it. He found beauty in every corner of physics, and he never stopped being amazed that the universe makes sense. The universe doesn't owe us sense. It doesn't owe us beauty. It doesn't owe us anything. But it gives us sense anyway. It gives us beauty anyway. It gives us rules and patterns and structures that we can discover and understand and use. That's not a cold universe. That's not a meaningless universe. That's a universe that rewards curiosity, that reveals itself to those who ask. That gets more beautiful the deeper you look. Particles don't exist, and that's the most beautiful thing I know. The universe is fields, all the way down, fields that ripple and oscillate and excite, fields that create temporary patterns called particles, fields that create persistent patterns called atoms, fields that create complex patterns called you and me. And we're just beginning to understand them, just beginning to map the mathematics, just beginning to see the structure. What more will we find? What deeper patterns? What more beautiful mathematics? We don't know, but we'll keep looking, keep asking, keep discovering, because that's what field excitations do. When they get complex enough, they explore the fields they're made of. They find the rules. They marvel at the beauty. And they share what they find with other field excitations. So the whole pattern can understand itself a little better. That's science. That's physics. That's the human project. Not comfort. Not simplicity. Truth. Beautiful, strange, mind-bending truth. Particles don't exist. And knowing that is better than any comfortable lie. Because the truth, however strange, is always more magnificent than the fiction, however familiar. That's what Feynman taught. That's what physics teaches. That's what the universe teaches. To anyone willing to listen. Are you listening?